Hey, hi everyone. So I don't know why less people joined this time, but hopefully this isn't a decreasing. So yeah, please come to the class, because I believe that coming to class has more effect in your understanding. Because you can have the opportunity to ask and also engage in the material. So by the way, so one thing that some of you might have thought that the two courses have much overlap. I believe no. So the only thing is that this illusion is because we are at the start of the two courses. Of course, when we want to start machine learning and deep learning, we start from the same things, and they have some overlap in these things. I understand that most of you guys have both of the courses, and I don't want this to be repetitive for you. But again, I'm emphasizing that I don't want to make them repetitive. The only thing is that sometimes, especially at the start, some things are repeated in the two courses because not everyone has both courses. So that's one thing. Another thing is that today we will cover overfitting and regularization. Okay. So in deep learning, we also have overfitting regularization concept. So the regularization things in the deep learning will have two things. One, the basic ones, which we cover here today. Also some regularization just for deep learning. But the basic ones, I'm gonna have an overview, fast overview in the deep learning course, and I will refer students of deep learning to watch today's lecture. I will make an announcement in the course link of deep learning. That's one thing. So what we are also recording will be used for deep learning course 2, but it doesn't mean that I'm not gonna cover basic overfitting for deep learning. I'm just gonna be fast in that session. Today we will be slow and for understanding, but in that session I will be fast, and then I will be slow in the regularization just for deep learning. Okay, that's one. So we were in the linear projection part. So I know that some of you have heard of this, but I'm gonna explain this for people who were not in the other course. So consider p basis vectors, okay, and we can define a p-dimensional Euclidean space by p basis vectors, right? For example, when we have two vectors, it defines a two-dimensional space, a plane. Three vectors x, y, z shows makes the 3D space, because every vector or every point in this space can be represented by a linear combination of those basis vectors, right? What do I mean by linear combination? I mean you multiply each of the basis vectors by a scalar, and then you add them up. When I say add them up, you might have -2, so plus minus something. Because the scalar that you multiply the vector by might be negative. That's one thing. For example, two vectors define a plane, and three vectors define a 3D space. That's one thing. In terminology, the p-base basis vectors span the two-dimensional Euclidean space, or the p-dimensional Euclidean space is spanned by the p basis vectors. That's one. Okay. Now consider the p vectors u1 to up, each of which is d-dimensional. Okay. These vectors can be stacked column-wise, so you can put them, because each vector is a column vector, we can put them together, so it becomes a matrix U d by p. The space spanned by the columns of matrix U is called the column space of matrix U. Did by this, right? Is it clear? So consider a space whose basis vectors are the columns of a matrix U, and that space is called the column space of U. We also have row space, by the way. That will be column space transpose. Okay, column space transpose. So in other words, the space whose bases are the columns of the matrix U is called the column space of matrix U. Okay. Now, assume there is a data point X, which is d-dimensional. The aim is to project this data point onto the vector space. By the way, the vector space is a space made of vectors. So spaces vectors are vectors. Span, and also a vector space has always the origin, because we already talked about it, because every vector minus itself should be in the or in the space. Spanned by p vectors, you want a up where each vector is a d-dimensional, and usually p is much less than d, usually. These vectors can be stacked again column-wise to make u. And so what we want to do, we want to project X onto the column space of U. If P is less than D, then we'll have a subspace. Sub is because it has lower dimensionality. The projection of X onto the column space is a P-dimensional, X is D-dimensional, then we'll have X tilde. But X is D by 1, right? U is P by 1. U is D by P. Therefore, U transpose is P by D. Therefore, the whole thing is P by 1. That's why X tilde is P dimensional. Right? And this X tilde is called projection, projected X onto the column space of U. Right? Okay. So the reconstruction of this is a d-dimensional. So X tilde is p-dimensional, but its reconstruction is a d-dimensional. So this is p by 1, U is d by p. This becomes d by 1. And we call it x hat. We can replace X tilde by U transpose X. Therefore, the reconstructed X is U transpose X. By the way, something that might be interesting for you. Assume U is a square matrix. Okay? Assume U is D by D. This I didn't tell in the other course. So assume U is D by D. Then what happens? U transpose X becomes again D-dimensional. You might be wondering, what does it mean? It's not subspace anymore. You're projecting a d-dimensional vector onto a d-dimensional space. What does it mean? If you think about it, you're just doing some rotation. You're just doing some rotation in the same space. You will be a rotation matrix, because I don't know if you have. If you remember, what was the formulation for the matrix of rotation? It was sine, cosine, something like that. Do you remember? You can look it up. And then you can see that's a matrix U, and that's a square matrix. Right? So it's kind of some rotation. If you P is equal to D, there is no projection onto a subspace. It's just rotation in the same space. If you have some addition, so U transpose X, that's some B bias, and B will be a d-dimensional vector also. Mean this. What is it? The whole thing? Yeah, B plus B is translation or moving. Yeah, right? So U transpose rotates that. B translates it. The whole thing together is called affine transformation. So when you can rotate and also translate, the whole thing is called affine transformation. That's one. Then we'll see in this course that PCA, if you don't truncate the columns, if you use the whole columns, P is D, then it means that PCA will be only a rotation. So consider this, because in PCA we'll use this. So consider a cloud of data points. Right? This is 2D. This is 2D, and assume these are the axes. Okay. Now, when I apply PCA, so on this, the matrix U will be 2 by 2. Okay. Then what happens if I consider only one of the columns of U, assume the first one, which is the most important one, then it will give me this. Okay. And if I project this, all of the data points onto this one-dimensional thing, they all can be seen. They will be projected on this line, and I can see it in this way. Just a bunch of scalar numbers, right? But if I don't truncate the matrix U and I use both columns of U in PCA, we will see that. What happens? So this is the first column. This will be the second column. I can see it in this way too. Because I don't care. This is the space, right? Whether I see it. What does it mean? This cloud of data is just rotating. PCA can be used for rotation or for the cancellation of rotation. Use that. So you can cancel the whole rotation so that the main axis becomes aligned with the variance of data. It also has been used for rotation. Even I can tell you that it has been used for cancellation of rotation in facial images. That's one. Another thing here is this. Consider this column space of U, which is three-dimensional. This is a two-dimensional point. You project it onto this column space. It will give us X tilde U transpose X, which is a scalar. But if you see it in the two-dimensional space again, it will be reconstruction. The difference between reconstruction and projection. We will have some reconstruction error, as you see here, because and we denote it by R residual. So X, this is X minus X hat. Why can't I say X minus X tilde? Because X tilde is p-dimensional, X is d-dimensional, and it's nonsense to minus between them. So X hat is d-dimensional. Then it will be X minus U transpose X. What happens if my data point is already in the column space, like this? The residual or the reconstruction error will be 0. And that's why in PCA, we'll see that. Assume that you have some facial images, you apply PCA to them. You don't consider the whole columns, you will truncate that. So we'll have some loss of information. We'll project onto the subspace, you reconstruct them back. Then you will see after reconstruction, some noises have been added to them. They are not equivalent to the original images. This is because of that loss of information, because of the reconstruction error. You get it? By the way, feel free to tell me things, talk to me. Okay, centering matrix. This wasn't in deep learning course, and that's used a lot in a statistical machine learning. What is that? Sometimes they denote it by C, but we denote it in this course by H. Okay, doesn't matter. Consider a matrix A, alpha by beta, which is represented by its rows. So, what do I mean by this? Its rows are alpha 1 to A1 to A alpha. Consider this transpose C. And also its columns are B1 to B beta. So it's alpha by beta. The size of A is alpha by beta. Where A, I, and Bj denote the ith row and jth column of A respectively. Okay? Note that the vectors are column vectors. Right. The left centering matrix is this. Defined. I'm defining that. Identity matrix, alpha by alpha, minus 1 over alpha. What is alpha? The number of rows. 1 over alpha. The vector 1, this means 1, 1, 1, 1, 1. The vector 1 transpose. What is 1, 1 transpose? It will be the matrix of 1. 1, 1, 1, 1, 1, 1, 1, 1, 1. all one. This is different from identity matrix. Identity matrix has only one in its diagonal. The other elements 0. Right? So identity matrix minus 1 over alpha times the whole matrix of ones. This is called the left centering matrix. Okay. Why do we call it centering matrix? Because we can use that in order to center data. What do I mean by centering data? Removing the mean. So you have some data points, you want to remove mean from these data points, the mean average of the data. Why do we want to do that? We'll see that, for example, in PCA. For example, this is one example. You might have any reason for removing the mean in your algorithm. But one example is this. You assume you have some axes, some cloud of points. A cloud of points like here. If you don't center, if you center the cloud of points, it will be like this, right? If you have removed the mean, and then PCA will give you these. Correct. If you don't center, what happens? I'm not centering these data points in the cloud. The PCA will give me this. Completely nonsense, something which is not important. Right? So we have to, in PCA, we have to center it. That's one thing. Okay. Left multiplying this matrix A is HA. So because we have matrices, the direction, it is important whether we left multiply or right multiply. Left multiply, it's HA. HA by equation 41 gives us this. Right? So I have this H and I'm also multiplying. So IA becomes A and also have this A, and this is the second term, right? It can be seen as this. It means that you remove the mean of the rows of A. What do I mean here? So consider this. This I mean. A transpose will get rid of this, becomes a column. Sorry, it will be A1 to A alpha, right? A1 to A alpha will have the mean of the rows. So mu rows means that column vector whose elements are the rows, means of the rows. Yeah, I think I need to explain more. This is A. Right? This is A1 to A alpha. Right? What is mu rows? Take the mean of this, put it here. Take the mean of this, put it here. Right?
We're replacing the entire row. We are replacing the entire rows with their
With the mean. Yes, exactly. I'm replacing the entire rows with their means. Yes, I think in Python it's np dot mean axis equals 1, I guess. Right? Across the axis 1, you take the mean. So this is mu row, and then I transpose it back in order to have this transpose again. So it basically, in simple words, it means that you have the matrix A, subtract every row by its mean. Okay. So HA removes the rows of the means of the rows. Okay. Just by one matrix multiplication. See? Beautiful. And mu rows also is the mean of the rows of the A. The right centering matrix is defined as this. Similar to that, but the size is different. So that was alpha by alpha. This is beta by beta. Now, if you have AH, you will have this. So you are the right multiply in the matrix H. So you will have A minus 1 over beta, A 1 transpose. By the way, this is here we had beta, here we had alpha. Okay, then this is you can see that it can be also shown by examples that this is equivalent to A minus mu columns. So basically it means that you have the columns of A. You subtract every column by the mean of the columns. You didn't get it. Okay. Okay, let me explain this. See, alpha by beta. Okay. I think one thing I said wrongly. So consider A alpha by beta. New rows. So this is a row, this is a row, this is a row. If I take the mean, I will have this. This is mu row. You get it or no? For example, an example. 1, 2, 3, 4, 5, 6. This is A. What is mu rows? 1 plus 4, 5 over 2, 2.5. 2 plus 5, 7 over 2, 3.5. 3 plus 6 is 9 over 2, whatever. So we have mu rows, okay? And then I will subtract every row by mu rows. So 1 minus 2.5, 2 minus 3.5, 3 minus 9 over 2, 4 minus 2.5, 5 minus 3.5, 6 minus 9 over 2. What is this?
I think it should be A minus mu.
No. See, this is the reason. Mu rows is a beta dimensional vector. And you see here alpha is 2, beta is 3. And this is also 3-dimensional. Okay, so mu rows is the mean of the rows. The mean of the rows, I think that's obvious. So you have several rows, take the mean of them. It will be beta dimensional, and then subtract every row by its mean, from its mean.
Isn't that like new column rather? Like we're like taking a particular column, right? Like each column.
No, the reason that I call it mu rows is that you have a bunch of row vectors, you are taking the mean of them. The naming is not important. Right. The thing is that HA does what I just showed. HA does this, okay? What is AH? What is AH? What is AH? Mu columns. What is mu columns? 1 plus 2 plus 3 over 3. 4 plus 5 plus 6 over 3. Okay, this is 2-dimensional. See here, mu columns is alpha dimensional. Here, then AH, what does it do? AH will be, assume this becomes 6 over 3 becomes 2. This is 10, 15 over 3 becomes 5. It's 2 and 5, right? 2 and 5. So AH means that 1 minus 2, 2 minus 2, 3 minus 2, 4 minus 5, 5 minus 5, 6 minus 5. Clear? Here by this example. Now, we also have HAH. This is called double center. What? Yes.
You subtracted A minus mu column. Would be A transpose minus.
Are you sure?
In the example. In the
42.
example,
Number 44.
In this example,
left hand side example, 1 minus 2.5. That is, you are doing A minus mu.
44
So
वाला
it will be A transpose.
this is the row. I'm subtracting this row from the mean of the row.
According to the equation, it should be A transpose minus mu. Right? Equation 42.
Okay, let me think.
When you take the transpose and it becomes like this.
No, the reason that I have this transpose is that because I want to subtract column wise. Because as I said, that I consider the vectors to be columns. The reason is only this. So if you have transpose of this, it will be 1, 2, 1, 2, 3 minus the vector 2.5, 3.5, 2, 9 over 2. Then you transpose it back again, it becomes like this. Right? I'm right? Okay. Did you get it? HAH, in simple words, what does it do? In simple words. I don't want to make it complicated. It removes the mean of rows, the mean of columns. It adds the total mean back. Why? Because when you remove the mean of rows and then the mean of columns, you're removing the total mean twice. You need to add the total mean once back. Okay. So again, you have A, it has some rows. Okay. You first subtract every row by its from the mean of the rows. It will be HA, I guess. Yes, it will be HA. Then you have these. This also has its columns. Remove the mean of the columns of the A from that. Then you will have these, some elements. This gives you HAH. However, you need to add the total mean, which is a scalar. Scalar. Get it? That the mean of all of the elements is a scalar. Each element is a scalar. So any confusion, because I think I explained it a bit bad, but I tried. Sorry about that. So this removes HA removes the mean of the rows. AH removes the mean of the columns. HAH is double centering, which removes the mean of the rows, removes the mean of the columns, adds back the total mean. Okay. The centering matrix is symmetric. There are some properties for the centering matrix. It's symmetric. Why? Because H transpose, you apply transpose on this. I transpose is I. Then 1 over alpha is also a scalar. Then 1 transpose, if you have this, we know that XY transpose reverses the order. Y transpose X transpose. So we'll have 1 transpose, which is 1, and this 1 transpose, right? By the way, this is H. So H transpose equals H. Therefore, H is a symmetric matrix. Okay. The centering matrix is also idempotent. What is idempotent matrix? It means that whatever you multiply it by itself, it becomes the same thing, right? So K times, if you multiply H together, you will get H. An example is H by H. If you multiply, this is H, this is also H. If you multiply the elements, the first element by the first element, the first element plus the first element by the second element, till the end, you will have this, you will get this line. Then what is this? These ones are alpha by 1. So this transpose will be 1 by alpha. This will be alpha by 1. And as they are all ones, this will be alpha. Right? You get it? 1, 1, 1, 1, 1, alpha times 1, 1, 1, 1, 1, alpha times. So this is alpha. 1 plus 1 plus 1 alpha times this is alpha. Okay, then this alpha cancels this 1 over alpha 2. So we'll have 1 alpha, and these two cancel each other. We'll have this, by the way, this is h. So when h is h, h is also h. So you can have it by induction, right? So that's the reason. So this is idempotent. Okay. We'll see centering matrix in a lot of machine learning algorithms. Definition, norm, very fast I go over these things because these are easy. So dot product defined as this, x transpose y is a summation of the product of the elements of x and y. They should be the same size, both d-dimensional. Inner product, also called dot product. We can have inner product for matrices defined as this. Is trace of x transpose y. Why do we need trace? Because x transpose y is a matrix here, and the output of the inner product should be a scalar. And so we need a trace operator, which is defined as the summation of eigenvalues of the matrix. Also, it can be proved that it's equivalent to the summation of main diagonal elements. Okay, it is defined as summation of products of the pairs of the elements of x and y. This is the inner product of matrices. Norm, very fast if I want to go. So its output is a scalar from Rd to R. It's a norm, it satisfies these. So it's always non-negative. If you multiply a scalar A, you will have absolute value. It can come out because of by absolute value. Why do we need absolute value? Because of the property 1. It needs to be non-negative. Also, if norm of x is 0, it's x is 0, and if x 0, norm of x is 0. We also have triangle inequality, which means that A, B, C, the distance, for example, the distance between A and C is always less than or equal to AB plus B, the triangle inequality. And the definition of distance metric is very similar to the definition of norm, because you can write the distance between x and y as the norm of x minus y. Okay. Some important norms. LP norm is defined as this. Summation of absolute values of elements to the power of p, then the whole thing to the power of 1 over p. P is greater than or equal to 1. L1 norm is this, and this is L2 norm. So if you set p to be 1, you will have L1 norm, and if p is 2, you will have L2 norm. If d is 1, L1 norm is just absolute value, right? Absolute. Frobenius norm, one of the important norms for the matrices, is defined as this. Its formulation is similar to the L2 norm for the vectors, but we should note that we also have L2 norm for matrices, which is not mentioned here. It's not L2 norm. Frobenius norm, its formulation is similar to the L2 norm for the vectors. Quadratic format, so we can write x transpose squared L2 norm of x as x transpose x, and if it is matrix, squared Frobenius norm of x as trace of x transpose x. So we'll get rid of the second root. That's one thing, and also we can use it in complex formats such as x minus y. What is it? So this is x minus y transpose x minus y. And if we simplify this, what will we get? X transpose minus y transpose x minus y, right? And this gives us x transpose x minus x transpose y minus y transpose x minus y transpose y. We can write y transpose x as x transpose y, because it's just a scalar, right? Then the whole this becomes minus 2x transpose y. Therefore, we can write it x transpose x minus 2x transpose y plus this is plus y transpose y. Isn't it familiar? It's very similar to this formula, a plus b squared. A squared plus b squared plus 2ab. If you have minus here, it will be minus here. I think it's binomial. Okay, yeah. So this is for scalars. This is in the vector format. We can have it in matrix format by Frobenius norm too. So that's an interesting thing. So the quadratic form is like a bowl. Like a bowl. If you look at it from above, it will be like this. These contours mean that they have the same function value. Derivatives very fast. I say that because many of you know that. So derivative of a scalar with respect to a scalar is a scalar. Why? Because whenever we say derivative of something with respect to something else, so whenever we say derivative of something with respect to something else, it means that that something else, whenever we tweak it, how will it affect the first thing? Okay. So derivative of a scalar with respect to a scalar is a scalar because whenever we change the second thing, it only changes the first thing once. So derivative of a scalar with respect to vector is a vector because whatever element of the vector we tweak, it changes the that scalar. Derivative of a vector with respect to another vector is a matrix. Whenever we change the elements of that vector, it changes every element of the first vector. So we'll have a matrix. It will be a matrix. Derivative of a vector with respect to a matrix will be a 3 tensor. Because whenever we change the elements of that matrix, it changes the elements of that vector. Right? Derivative of a matrix with respect to another matrix will be a 4 tensor. Like that. When I say a 4 tensor, I mean tensor with rank 4. Okay, gradient and Hessian. Gradient is just derivative, but in the for the vectors. And when we can have the derivative of in the matrix format too, that will be usually called Jacobian. You can also have Hessian. Hessian is a, by the way, why is gradient usually a vector? Because the function is a scalar. Derivative of a scalar with respect to a vector will be a vector. So that's why gradient is a vector. Why is Hessian a matrix? Because when the Hessian can be seen as a derivative of gradient with respect to that vector. Gradient is a vector. That vector is also a vector. Derivative of a vector with respect to another vector is a matrix. That's why. Chain rule, I think you all know that. Some examples here. We can also have these operators, vectorization and devectorization. So sometimes, why do we need that? Especially when you have derivative of matrix with respect to another matrix. I said it is a 3 tensor. How do you write 3 tensor in mathematics? It's very hard. Okay. So they usually vectorize it. They vectorize it. They do the operations, the multiplications of the derivatives and chain rules and everything. At the end, they devectorize it. You get it? No? I have some examples, but I think I removed them. So I can put some examples on the course link. Right now, I don't have them on top of my mind. But for example, briefly, if I want to say that, I think derivative of, for example, AXB with respect to X. AXB, A is a matrix, X is the matrix, B is a matrix. There is no trace here. So the numerator is the AXB is a matrix. The variable X is also a matrix. This gives us a 4 tensor, right? But it's very hard to write a 4 tensor. What do we do? They write it in using vectorization. So the result will be a vector. So they put, what do I mean by vectorization? So this is a matrix, we have elements, right? Then I can put the first row here, the second row here, third row here. This is a vectorization. The vectorization means that I take this, I put it in here. I take it, I put it here, also here. Yeah, it's the devectorization. Therefore, using this technique, you can handle all tensors. So don't care how many rows and columns you have. You put them one by one and it becomes a vector. Simply, you do your calculations and at the end you devectorize. For devectorization, we need the size. We need to know how much we should go and then cut. Right? For vectorization, you don't care. Just put them. You just concatenate, right? Optimization. So consider minimization of a function f of x subject to M1 inequality constraints and M2 equality constraints. In simple words, I can write it as f of x plus penalties, soft penalties on not satisfying the constraints. This is called Lagrangian. And we can solve the optimization problem by taking derivative of Lagrangian with respect to variable and setting to 0. Okay. Similar to what we did in high school, when we didn't have any constraint, we take derivative of function with respect to that variable and set it to 0, right? So for more information, you can watch the optimization techniques course. Unconstrained optimization, when we have this, we don't have any constraints, then we can say we do it iteratively. So whenever we have f of x equals 0, f of x, in numerical analysis, we know that this means f of x equals 0 means that let's find the roots of the f of x, right? For finding that, we can set f of x to 0 and then calculate, rearrange the things, and hopefully we can find x in a closed form solution. If we can't do that, we need to do find the roots by numerical analysis, such as Newton-Raphson method. Likewise here, in optimization, we don't have f of x equals 0. We have gradient of f of x equals 0. And hopefully it gives us the closed form solution. Otherwise, we need to do it numerically or iteratively. We have first order numerical optimization. We also have second order. First order is gradient method. Second order is Newton's method. First order uses gradient and second order uses both gradient and Gaussian. We can also, for constraint, we can use interior point method and proximal methods, etc. You can see the optimization course for more information. Rayleigh-Ritz quotient. Okay, this wasn't in deep learning. So this is also required in statistical machine learning. What is that? So Rayleigh-Ritz quotient or Rayleigh quotient. Okay, but you see this a lot in statistical machine learning. A lot. It's kind of dominating that. So see what is that? I denoted by R, A, and X. It's X transpose A, X. A is a matrix. X is a vector, right? X transpose AX over X transpose X. This is defined as this function called Rayleigh-Ritz quotient. R stands for Rayleigh-Ritz or Rayleigh. And quotient here means that just a fraction, right? Okay. Where A is by the way, in mathematics, we use quotient for two use cases. One of them is fraction like this. There is also quotient to space, which is in pure math and in differential geometry. I'm not talking about that, okay? So have in mind that quotient has two meanings in mathematics. One is in pure math and in differential geometry, quotient to space. The other one is just fraction. Here it means that fraction, okay? So RAX is defined as X transpose AX over X transpose X. As you see, they are both numerator and denominator are quadratic forms, right? Okay, A is a symmetric matrix. X is a non-zero vector. Why? Because I don't want to have zero division by zero. So A is also, as I said, symmetric. X is non-zero vector, right? One of the properties of Rayleigh-Ritz quotient is this. Doesn't matter if you multiply X by a scalar C. Doesn't matter. C is a proof. if you put Cx rather than x in this. What's that? It doesn't matter if you put Cx in this equation 48, doesn't matter. So you will have this, by the way, C transpose is C, doesn't matter. So you will have this, and you can bring this C here. This is a scalar. You can move it in the multiplication. Okay, so you have C squared here. You also have C squared here. They cancel each other. You will get this. You don't care if you multiply x by a scalar. That's one. That's one thing. Another thing. Consider optimization of Rayleigh-Ritz quotient, because in statistical machine learning, we usually maximize or minimize a Rayleigh-Ritz quotient. Okay. According to equation 50, it is equivalent to the following. So you can write it in this way. So you can add a fake constraint, and this equation 52 is equivalent to equation 51. Well,
I understand like what Rayleigh-Ritz quotient is, but where do we use it? Like, why are we learning it? Like,
because PCA, Fisher discriminant analysis, some other things I need to remember, but one of them is Fisher discriminant analysis. An example is that, because we'll see that this is Rayleigh-Ritz quotient, and for example, A, the covariance matrix. Okay. If you set A to be covariance matrix is also symmetric, right? If you said that this will be maximization of x transpose A x over x transpose x is PCA. We'll show that. I will show that to you why it is PCA. Now we'll have also generalized Rayleigh-Ritz quotient. We'll see that in a few slides. That's Fisher discriminant analysis. So in Rayleigh-Ritz quotient, just for the sake of motivation, he said why we need that. I'm giving you some examples. The generalized Rayleigh-Ritz quotient is this. Where was that? Okay, it's here. So we have A and B also in the denominator. If you set A to be the variance between classes, if you set B to be the variance of each class, the summation of variances of classes, A is the variance between classes. It will be, and you maximize that. What does it mean to you? So maximize x transpose AX over x transpose BX. A is the variance between classes, B is the variance of within classes.
we shorten the variance between
What?
inside the class. We
Maximize this. It means what? Maximize the numerator, minimize the
value of A goes up and value of B goes down.
exactly. Because we're maximizing the whole thing. So we're maximizing numerator, minimizing the denominator. So far clear?
Yeah.
Yes. Now, what? By the way, when you set A to interclass variances and B to within class variances, this generalized Rayleigh-Ritz quotient is called Fisher criterion. Okay. And when you maximize the Fisher criterion, as he also said, you're maximizing the numerator, minimizing the denominator, maximizing the variances between classes, minimizing the variances within classes. This is exactly the idea of dimensional reduction. Do you remember I said we want to discriminate classes better? That was just for motivation why we are learning this. I know that you might say, why do we learn these things? Seems that they are not related to machine learning. They are actually related, completely machine learning. Okay, that's one thing. And so equation 51 and 52 are equivalent. Why? Let's prove. We can let y be normalized x. So x over normal, like a normal. Okay. Then what happens? The Rayleigh-Ritz quotient of RAY is this. Y transpose AY over Y transpose Y by definition. Then replace Y with its definition here. What do we get? 1 over norm of x, they are scalars, they can come out. So we'll have 1 over a square L2 norm of x, y, because we have 2 of them in y transpose and y. Also have 2 of them here in the denominator, so they cancel each other. We'll have x transpose ax over x transpose x, which is r of a and x. So r of ay equals r of ax. Also, we know that a squared L2 norm of y is 1. Why? Because y, we also define that to be normalized x. So if you put this here, you'll have a squared L2 norm of y. This 1 over L2 norm of x is a scalar, can come out of norm. But do you remember the properties of norm? We just saw that. That's why I'm saying that take the preliminaries seriously. Where was that? It's here. Property 2 of norm. We have a scalar in the norm. When you bring it out, you will have absolute value, but we have a squared L2 norm, so it becomes a square. Okay. Let me come back to where we were. Okay, so we'll have this a squared 1 over a squared L2 norm. Well, we have also a squared L2 norm because we have here by this definition of y. Then these two cancel each other, it becomes 1. So as squared L2 norm of y is 1, L2 norm of y is also 1. Okay. We know that norm is non-negative. It can be minus 1. So it means that now we are, it's like we are having optimization of r of a and y with respect to subject to again, let me write it down. I think you will understand it better. Subject to norm of y is 1. Here, this is a fake constraint. Why? Because it's already satisfied. We just proved that it's already satisfied. So I can put it as a constraint, right? So far clear? Now, y is a dummy variable. I can call it table. Mean max of R, A, and table with respect to table, subject to this L2 norm of table is 1. I can call it table X. So I will get equation 52. You can change the name of dummy variable, right? Whenever I say dummy variable, it means that the name of variable is not important. You can replace it by Benjamin, okay? So another thing is that equation 51 is also equivalent to saying that minimize, maximize x transpose ax subject to this. So the constraint is the same as before. However, we can get rid of the denominator in the Rayleigh-Ritz quotient. Why? What was the denominator of Rayleigh-Ritz quotient? It was Rayleigh-Ritz quotient was this, right? Constraint is L2 norm of x is 1. So a squared L2 norm of x is also 1. So x transpose x is also 1. So this denominator is 1. Clear? Do you follow me? Yeah. Okay. So that's why we can get rid of the denominator. Now, generalize Rayleigh-Ritz quotient or generalize Rayleigh quotient. This x transpose ax over x transpose bx. Both quadratic form. A and b are both symmetric, and x is non-zero. What happens? If the symmetric b is positive definite, what does it mean to be positive definite? It means that its eigenvalues are all greater than 0. Right. It can be proved that a positive definite matrix can be decomposed by Cholesky decomposition. It is a decomposition, matrix decomposition in linear algebra. Don't need to worry about it. Okay. And what is that? It's C transpose, where C is a lower triangle matrix. What do I mean by lower triangular matrix? Is that we have elements here, and these are all zero. Okay. In case B is this, then we can write, we have this equation 58. Generalized Rayleigh quotient of A, B, and X is equal to Rayleigh quotient, Rayleigh quotient of D and C transpose X. Proof, where D is defined as C inverse, AC inverse transpose. Okay. Why do you look at me like that? Is everything clear? Ask me if you didn't understand anything. Ask me. So what do I mean by C inverse transpose? It means that take inverse and then transpose it. So C inverse transpose, I can write it as C minus T, right? Or you take the transpose and then take inverse, doesn't matter, okay? And then, so that's one thing. Let's prove it. Let's prove it. Why? I start with right hand side and I will end up with left hand side. Right hand side is Rayleigh of D C transpose X. By definition of Rayleigh quotient, I'm just putting this here, here, right? Everything clear. Okay. Equation 59, by definition of D, which I defined, I replace this D by equation 59. Clear? Then I will, so this is D, by the way. This is D. I think I need to show you one step to understand. So what is this C transpose X? Transpose C inverse A, C inverse D, C transpose X. Numerator, okay? Here, this is exactly D. This is D, right? Then, do you agree that I can write it in this way? C inverse T? Because transpose reorders, changes the order. Okay. I can write it X transpose C exactly here. So I think now I showed you here. Here. Then because of equation 57, because of the Cholesky decomposition, we know that C inverse is C is a square matrix. C inverse is I. I think you in linear algebra, you know that C inverse C is I, right? C inverse, is it I? Only if it's a square matrix. So C inverse C is I. C inverse is I only if it is a square matrix. Let's jump back to orthogonality, because these are important concepts in linear algebra. You remember I said U transpose U is I for orthogonal matrices. Why? Because in orthogonal matrices, U transpose is U inverse. U transpose U becomes U inverse U. So it's I. U inverse U is always I for all matrices, but U transpose becomes U inverse only for orthogonal matrices. So U transpose U is I for orthogonal. But I also told you, U transpose in orthogonal matrices becomes I if it's only a square matrix. And why is that the case? Because U transpose in orthogonal matrices becomes U inverse. And U inverse for square matrices is I. Always. Okay, that's one thing. So because of this, it becomes this, and this is, by the way, generalized Rayleigh quotient, which is left-hand side. Also, likewise, we can have multiply in generalized Rayleigh quotient, we can multiply X by a scalar C. Okay. And you will have this. By the way, I will not ask you any proof of these things in the exam. You don't need to what, just forget about the exam and try to understand what I'm saying. Okay. So this now optimize generalized Rayleigh quotient of A, B, and X. What is it? We can, similar to what we had for Rayleigh quotient, with the same proof, with the similar proof, you can have X transpose B X equals 1. Okay. And one more important thing, does it matter if I set X transpose BX also in Rayleigh quotient X transpose X equal to 1? Can I set it to equal to 2? Equal to 3? Equal to 1.5? Equal to -1? Doesn't matter. Do you know why? First off, because of the proof. For two reasons, I'm saying that it doesn't matter. Because of the proof. Really, let's go back to where we said we can have this. It doesn't matter for several reasons. I think the most important, one of the reasons is that inside the proof steps, you can see that it doesn't matter. Another reason, which is the simplest reason. When we want to solve this, we form the Lagrangian. We just reviewed that in a few slides ago. What is the Lagrangian? X transpose AX plus lambda, some dual variable. X transpose B X minus 1. Okay. This is Lagrangian, nothing complicated. So I'm saying that this is the objective function. This is the constraint, right? So because I can write it in this way. This is a constraint. I multiply it by some scalar. This is called dual variable. Doesn't matter, okay? Then I said, do you remember I said we take derivative of Lagrangian and set it to 0. If I take derivative of Lagrangian with respect to x, this one goes away. This is a scale, it's constant. This is a constant with respect to x. Does it matter if the constant is 1 or 2 or -1 or 1.5 or Benjamin or table? Doesn't matter, right? That's the thing. So you can set X transpose BX or X transpose X in Rayleigh quotient to anything. That's one thing. And by the way, Rayleigh quotient is a special case of generalized Rayleigh quotient if you set B to identity matrix. Right? I think now you understand. Okay. Well, it's used a lot in machine learning. Eigenvalue and singular value decomposition. I'm aware that I said some parts of it in the deep learning course. I'll be fast in those parts for you not to be repetitive. However, this section has some other thing which we didn't cover in deep learning course because that's not required for deep learning, but required for statistical machine learning. And that's optimization forms of eigenvalue problem. So what optimization problems will end up with eigenvalue problem or generalized eigenvalue problem? By the way, I wrote a tutorial paper on that. Has been cited a lot by different people from different fields of science. I didn't know that it is used in physics too. Many people in physics are using that. Many people in telecommunications are using that. So it's very useful for various fields of science, okay? So let's see. As I said, it has many important roles in different fields of science, such as machine learning, physics, statistics, mathematics. Why? Because of this. What are eigenvectors and eigenvalues? So when you have some matrix, the eigenvectors show the most important and informative directions of the matrix. So this matrix shows some important directions, some maybe hypothetical space, okay? So it has some important directions, information directions, I'm saying that. And eigenvalues show that in that direction, in each of the eigenvector directions, how important that direction is. An example for you to understand is covariance matrix. Consider the covariance matrix. What are the important directions of the covariance matrix? It's just the direction of variance or spread of data, because this is a covariance matrix, right? So if you, for example, if you have a cloud of data points, the first eigenvector of the covariance matrix of these data points, by the way, these data points are 2D, right? 2D, two-dimensional. So the covariance matrix is 2 by 2, right? So you will have two eigenvectors, right? The first eigenvector will be this, the direction of spread of data. The second eigenvector of covariance matrix is this, because this is the second direction of spread of data. And this, the eigenvalue corresponding to the first eigenvector is larger than the second eigenvalue, because we have more spread of data in the first direction. Eigenvalue problem can be written as this. A phi I, lambda I, phi I. Phi i's are the vectors, eigenvectors. Lambda i's are scalars, eigenvalues. We have d of them because if matrix A is d by d, we have d eigenvectors and d eigenvalues, right? In matrix form, we can write, so this is d of them, right? D equations. We can put them together to become a matrix form, and we have this A phi equals phi lambda. Phi is d by d. If you put them column-wise next to each other. And lambda is d by d diagonal matrix whose diagonal elements are the eigenvalues. Okay? Consider the eigenvalue problem. Right multiply phi transpose from to the sides. We'll have phi transpose as we haven't truncated phi. And we know that phi is because the matrix of eigenvectors is orthogonal. We know that this is one of the properties of eigenvalue decomposition. We know that phi is orthogonal, so phi transpose equals phi inverse. Phi inverse is I identity. Why? Because we haven't truncated that. So this will have A. We also have phi lambda phi transpose or phi lambda phi inverse, doesn't matter. This is called eigenvalue decomposition. Also called a spectral decomposition. Okay. If you wanna use eigenvalue decomposition, you can use libraries. Don't need to do it because there are some methods to solve eigenvalue decomposition. We are not going to cover those. Those are linear algebra, such as power method and these things. But in our cases, we will use libraries like learn SciPy in different languages. Okay. Generalized eigenvalue problem is this. We'll have a matrix B also here. In matrix format, we'll have A phi equals B phi lambda. Phi is d by d, and lambda again is d by d, eigenvectors and eigenvalues. We have a pair AB, called pair or pencil. And also we have you can call it, call the phi and lambda as the eigenpair of pair A and B. Okay? You can see that eigenvalue problem is a special case of generalized eigenvalue problem if we set B to be I. Okay? This wasn't in the deep learning course, please note. Okay, optimization form 1. Maximize phi transpose A phi subject to phi transpose B phi equals 1. Didn't we see that? Where was that? This optimization form. Did we see that? This is, you said that. This is general optimization of generalized Rayleigh quotient. We decided a few minutes ago, right? Now, do you see why PCA ends up to eigenvalue decomposition of covariance matrix? Because of this. PCA, I just said, can be seen as a Rayleigh quotient. And we are going to prove that optimization of Rayleigh quotient ends up to eigenvalue problem. That's why PCA ends up to eigenvalue problem. That's why Fisher discriminant analysis, FTA, ends up to generalized eigenvalue problem. Because of this, we are proving that. Okay? So, phi transpose A phi subject to phi transpose B phi equals 1. A is d by d, B is d by d. Lagrangian of this. We have this. We have phi transpose A phi minus lambda phi transpose B phi minus 1. Take derivative of with respect to phi because phi is a variable here, right? Set it to 0. We'll have 2A phi minus 2 lambda B phi. You might be saying that why isn't the derivative of this phi b? Why is it B phi? Can anyone tell me? So derivative of phi transpose. Sorry about. Give me a sec. Sorry about that. So. Okay, sorry about the issue that happened. Sometimes I forget to do that because there is a timer on this. If I forget, please remind me. I need to set it to 4 hours, something like. Okay, so I was asking you this. This is an important thing, and I want you to understand it. This is also related to derivative. Assume I'm saying that derivative of, because we are using that in that slide. Derivative of phi transpose b phi with respect to phi, sorry, with respect to phi. Okay. This is a trace of that. Trace of this. So the numerator is the scalar trace of phi transpose b phi. Okay. What we are taking derivative with respect to is phi, which is 5/10 is a matrix. Okay. So derivative of a scalar with respect to a matrix is a matrix, and its size should be the same, right? So phi is 5. Oh, by the way, now I know that phi is a matrix. I want to make it harder, as I said. So this is phi is a matrix, assume, and it's d by d. Okay, it's a d by d thing. B is d by d. Phi is d by d. I know that this should be derivative of a scalar with respect to matrix is a matrix. I know that. I also know that this is a quadratic form, right? So when you say derivative in a scalar world, when you say derivative of 2x, x transpose x is like 2x, right? When you say derivative of 2x, no, sorry, x squared, x transpose x is like x squared. Derivative of x squared with respect to x is what? 2x in a scalar. Now, similar, it should be, we should have similar format in the matrix world. So I know that it should be something like 2b phi, 2 phi b, 2 b transpose phi, 2 phi transpose b. So because I have some b here, a pain in the neck, if I didn't have b, derivative of trace of phi transpose phi with respect to phi, I know it would be 2 phi, then, right? Even in the matrix form, I have a pain in the neck, which is b. I need to include it somehow, and I know it should be like 2 phi. So it's either 2 b phi, 2 phi b, 2 b transpose phi, 2 phi transpose b. What I'm telling you is the result of me thinking for, I think, 2 days. Okay, so now I want you to tell me which one is correct. So one thing, first off, for the technique is this. First off, I don't care whether phi is d by db is d by d, because as I said, in derivative in matrix multiplication, the dimensionalities should match. Do you agree with me? Yeah. Okay. But if I set the dimensionalities of phi and b and these to d by d, all of them, then I will get confused. Which d? The first d rows or d columns? That's why I make fake dimensionalities. Fake dimensionalities, but they should match. For example, I know phi is supposed to be a square matrix, but I don't care. I say let it be 5/10. 5 rows, 10 columns. So phi here is 5/10. Phi transpose is 10/5. B needs to be 5/5. Has to be. Also, it doesn't falsify the property of trace. I know the input of trace needs to be a square matrix. It is 10 by 5, 5 by 5. 5 by 10 is 10 by 10. That's correct. Although I made fake dimensionality, this is correct. Now it makes my world easy in order to understand which one is correct. To B is 5 by 5. Phi is 5 by 10. This is mathematically correct. Some of them are mathematically correct. This is not. This is not mathematically correct. 5 by 5 cannot be multiplied by 10 by 5, right? This is correct. 10 by 5, 5. Which one of these two is correct? After we remove the non-mathematical nonsenses, we'll have mathematical sensefuls. Now let's choose among them. Which one? This is 5 by 5 times 5 by 10 becomes 5 by 10. This 10 by 5 times 5 by 5 becomes 10 by 5. We know that we are taking derivative with respect to 5, which is 5 by 10. So it needs to be 5 by 10. Therefore, this is correct. You see the blue. In this technique, if they give you a matrix format, very hard, very complicated derivatives, you don't need to look at the cookbooks, because there are some matrix cookbooks. If you can search, there are thousands of pages. Then if you don't know this technique, you need to go to the cookbooks and see, okay, which line, by the way. With that, we can get rid of the cookbook and do this technique and calculate the matrix, the derivatives. Okay, now let's use the same technique. Here, phi is a vector. It's easier, actually. It's not a matrix. Easier. But again, we can make fake dimensionalities, as I said, and we'll see that derivative of phi transpose b phi, there is no trace here because it's a vector. Phi is a vector here. Is 2 actually b phi. B phi is correct. 2b phi. 2 is because it's quadratic form, right? Then when you set it to 0, these 2's cancel each other. You'll have a phi equals lambda b phi. What is it? It's generalized eigenvalue problem, which we saw. So this optimization problem is actually ends up to a generalized eigenvalue problem, right? By the way, here we have maximization. Here we have maximization. And we can have minimization too. But this is only one eigenvector, phi, because this is a matrix, right? One eigenvector, one eigenvalue. We can have several eigenvectors, eigenvalues. In this way, we have now we need trace in order to make it scalar. Phi transpose a phi. Let's write the Lagrangian. We'll have these. Take derivatives of Lagrangian with respect to phi. I know phi is d by d, but in order to calculate derivative, let's make fake dimensionalities in our minds. And we'll see that actually the correct derivative is 2b phi lambda. Okay, of this. And then set it to 0, you will end up with this. What is this? This is generalized eigenvalue problem when we have several eigenvectors, eigenvalues. Now, here it's important whether it's minimization or maximization, because we have several eigenvectors and eigenvalues. If it is maximization, we sort the eigenvectors by largest eigenvalue to smallest eigenvalue, because you can sort the eigenvalues, right? There are scalars. Eigenvalues are scalars. Also, eigenvalues are corresponding to eigenvectors. You know that too, right? So put the eigenvector with the largest eigenvalue at first, and then come down, descend in order, because it's maximization. The largest is more important. If it was minimization, the other way around, ascend in order, sort them. The smallest eigenvalue to a largest eigenvalue, and also their corresponding eigenvectors. You get it? And what do I mean by sorting? Phi has columns, right? And eigenvectors. Sort the columns, I mean. Also, lambda is diagonal, has eigenvalues. Sort the eigenvalues in the diagonal. Another form, optimization format, is this. Minimize Frobenius norm if it, by the way, here X is a matrix. If it was a vector, rather than Frobenius norm, we would use L2 norm, okay? So minimize Frobenius norm squared, X minus phi transpose X. Here, phi is a vector. We will see its matrix format too, okay? What is it? Let's simplify it. Let's simplify it and see. Do you remember quadratic format? Recall several slides ago in the preliminaries. Right, so this transpose this. This transpose also can be applied on this. And when applied on this, it reverses the order in the multiplication. Right? So because X transpose, phi transpose becomes phi. This phi transpose. Then we'll have this, then multiply elements to each other. The first by first, first by second, second by first, second by second. You will have this. Here, this appears, phi transpose phi. By the way, this is a constraint. It needs to be satisfied. Therefore, I can replace phi transpose phi by 1. Right? Then I will have this. Because this becomes X transpose phi transpose X. We have minus 2 of them here. Cancel each other. We will have one of them, minus 1 of them. Then trace of A plus B becomes trace of A plus trace of B. It's a linear operator. So we'll have this. Then there is one property in trace. That's called cyclic property. And what do I mean? Trace A, B, C, D. You can bring D here. One by one, you can bring one of the elements to the first. So it's like a cycle. See? So you can write this as trace of D, A, B, C. You can write it as trace of C, D, A, B. You can write it as trace of B, C, D, A, etc. Cyclic property. Okay. If I do that, then I will have this. Also, as it is linear operator, I can write it back to like this, trace of this. So the Lagrangian is this, which we simplified, minus lambda the constraint. Okay, where lambda is the Lagrange multiplier or the dual variable. Okay, now let's take derivative with respect to phi, which is the optimization variable, set it to 0. This is quadratic format, but it's constant with respect to phi. I don't care. This, I'm taking derivative with respect to phi. This is quadratic format. And using the same technical fake dimensionality, you can see it becomes 2xx transpose phi. By the way, you can see x transpose as y, something like that. Y phi transpose. We know it's a quadratic format. So it should be something like y phi y transpose phi transpose y. Using fake dimensionality technique, you can see it's actually y phi or x transpose phi. We have 2 also here because it's quadratic format. Minus 2 lambda phi. Set it to 0, you will have this. Now you can see this as something like y or a, doesn't matter. By the way, this is if you eigenvalue problem for xx transpose. Right? For xx transpose. This is eigenvalue problem. By the way, what does it mean? Let's interpret equation 70. That's minimization of reconstruction error. What is inside Frobenius norm? See phi as u. Recall several slides ago when we were talking about projection and reconstruction. Don't you remember? And in projection, we had phi u transpose x. Reconstruction was u transpose x. We also have it here, x minus u transpose x. And that's the reconstruction error. Now, what if the question is this? Find some projection matrix. I want to project some x onto its column space, but I want the reconstruction error to be minimized. If you solve this, you will see it's an eigenvalue problem. We will see that it's actually PCA again. So you can formulate PCA in 2 ways. Either we will see that. Either in this way, equation 68, or in equation 70, which is minimization of reconstruction error. So we can prove that PCA minimizes the reconstruction error. Okay, now optimization for form 4. The same thing, but for the matrix form. For the matrix form, okay? So we have these square Frobenius norm. If with the same proof, with the similar proof that we had in the previous slide, we can see that this is equivalent to this, okay? Now Lagrangian is the objective function, this minus, this is this is the constraint, and this is lambda is the Lagrange multiplier. Take derivative with respect to phi, set it to 0, you will end up with this. So it is an eigenvalue problem for XX transpose again. By the way, here we have several eigenvectors because phi is a matrix. Now consider this maximization of the generalized Rayleigh-Ritz quotient. Okay. We just saw that several slides ago. It's equivalent to equation 73. Lagrangian is this. Take derivative, set it to 0. It becomes this. Yeah. No, I didn't explain this. This is a new thing. I didn't explain this. I know they end up with the same thing. And these are different optimization problems which end up to the same thing. Singular value so optimization of eigenvalue decomposition is over. This wasn't covered in deep learning course. Now SVD, I covered that. But let me go here. See? Singular value decomposition. What is that? It's one of the most well-known and effective matrix decomposition. By the way, when I say matrix decomposition, what do I mean? Assume I have some matrix. Listen to me. I have some matrix. I decompose it to multiplication of several matrices. So I have a matrix X. I say it's equal to ABC, but it needs to be equal. There are different ways in linear algebra to find the decomposition. Some decompositions decompose into two matrices, multiplication of two matrices, some to 3. Some decompositions are, some well-known decomposition methods are Polsky decomposition, which we saw several slides ago. Eigenvalue decomposition or spectral decomposition, which we also saw several slides ago. One of them is singular value decomposition, which is this. Okay. What is this? We have two types of, by the way, SVD is always like this. So we have A, we decompose it into A sigma V transpose. Okay, and U sigma V transpose. Assume A is alpha by beta. In eigenvalue decomposition, usually, not necessarily, usually the matrix is a square matrix. In SVD, the matrix doesn't need to be a square necessarily. It can be rectangular. So alpha by beta. Then in the complete SVD, U is alpha by alpha, V is beta by beta, sigma is alpha by beta. Okay, so U and V are square, sigma is not. U is has the left singular vectors, V has the right singular vectors, sigma has the singular values. Okay. By the way, when I'm introducing this SVD as well as EVD, I'm not saying how to solve them because there are libraries to do that. You know, in order to know how to solve these, how to find U sigma V, you can go to linear algebra courses. Okay, this out of the scope of this course, but I'm introducing them to you because we use them. Okay, so U has left singular vectors, V has right singular, and sigma has singular values. And as I said, sigma here is a rectangular, but it's diagonal. So it's either these, if alpha is greater than beta. If alpha is less than beta, then we have this. Sigma 1 to sigma alpha or sigma 1 to sigma beta. Okay. And U and V, which have the left and right singular vectors, they are orthogonal matrices. This is one of the properties of SVD. Okay. And by the way, here, now we have incomplete SVD. That was the complete SVD. This is incomplete SVD. So incomplete SVD, the same format. However, the dimensionality of U and V and sigma differ. So U is alpha by K, V is beta by K, sigma is K by K, where K is minimum of alpha and beta. Okay. And sigma is actually a square matrix here, which is sigma 1 to sigma K. Okay. The beauty of here, U and V, as I said, are orthogonal matrices. So U transpose equals U inverse. V transpose equals V inverse. Therefore, U transpose U and V transpose V are always I. However, if we don't truncate U and V, it means that if we consider all of the columns of U and V, it means that U and V will be square matrices. Then U transpose and VV transpose are also I. If they are not square matrices, they are not I anymore, these two. But these two always, equation 77 and 78 always are true. There is a relation between SVD and EVD. So consider AA transpose. Let U sigma V transpose be the SVD of A. You will have this, transpose, right? You can apply transpose on this, it reverses the order. So you will have V transpose becomes V. We'll have sigma transpose equals sigma. Why? Because it's a diagonal matrix. You will have U transpose, which is here. VV transpose, by the way, is I, because it's orthogonal matrix. We'll end up with sigma. Sigma is sigma squared. So you can write it. What is this? It's actually an eigenvalue problem. We saw that. Eigenvalue decomposition or a spectral decomposition. So you can say that U, which has the left singular vectors of matrix A, can be seen as the eigenvectors of AA transpose. Again, I repeat. U has the left singular vectors of matrix A, can also be seen as the eigenvectors of AA transpose. And sigma squared, had the singular values of A. Sigma squared can be seen as the eigenvalues of AA transpose. Now let's see A transpose A. We'll have A transpose A. These are the singular value decomposition. U transpose becomes I. You will have this V sigma squared V transpose. And this means that V, which has the right singular vectors of A, can be seen as the eigenvectors of A transpose A. And sigma squared also has its eigenvalues. Interesting. So there is a relation between SVD and EVD, eigenvalue decomposition. Some acknowledgement, and then we go to the next slide deck. By the way, why do I will go and show the references too? Because I always, whenever I watch YouTube videos, when they explain and they say see reference something, and at the end they don't show the references, I want to kill myself. Because I want to see that reference. Therefore, I will go over the references very quickly too. So some slides are based on this textbook, Elements of Dimensional Reduction and Mindful Learning. Reference 1. Some slides of this slide deck are inspired by Professor Muzhu at the University of Waterloo, Department of Statistics. The expectation parts. For more information on optimization, refer to my course Optimization Techniques at the University of Guelph in this YouTube channel. For more information on Rayleigh-Ritz quotient, eigenvalue problem, and SVD, you can see our tutorial paper, Eigenvalue and Generalized Eigenvalue Problems tutorial. More information on expectation. We have 2 tutorials, also theory behind overfitting, cross-validation, regularization, bagging, and boosting. Also sampling algorithms from survey sampling to Monte Carlo methods, tutorial and literature review. These are good tutorials, I believe can be useful. So quickly going through the references. This is the book of ours on dimensional reduction and manifold learning. Also, this is Reference 2 is for a survey on prototype selection. Do you remember we went over that? Also for prototype generation, this is a survey. This is my thesis, which can be, has dimensional reduction and numerosity processing. This is for eigenvalue problem. You can see this. Also Rayleigh principle. So as I said, Rayleigh-Ritz quotient can be seen in this technical report. Also, there is a book on principal component analysis. Also, it is an important book actually, published by Springer. Also, this is algebraic eigenvalue problem, talking about eigenvalue matrix computations by Golub. This is one of the important books in matrix linear algebra. What you want to ask some? This is an important book by Golub, matrix computations. If you want to see the history of singular value decomposition, you can take a look at this reference. Also, singular value decomposition and least squares solutions, how to solve SVD, eigenvalue and generalized eigenvalue problems, our tutorial on EVD and generalized EVD, the theory behind overfitting cross-validation. This is the tutorial, also our tutorial on sampling algorithms. Okay. Let's go to the next, which is overfitting error. Yes. Okay. So overfitting, cross-validation, and regularization. Now preliminaries are over. An important concept in machine learning. These are important concepts, basic fundamental concepts. I can say if in industry also, when you go and take an interview, there is a high probability that they ask questions relating to this. First, measures for a model. Assume we have a function f, which gets the input xi and outputs some f of xi. So I have some model, it gets some xi as input. This model is f, called f. I don't know this model. This is in the ideal world, okay? Some model, the ideal world, gives me f of xi, or also called fi. This figure also shows this. We wish to know the function, which we call it the true model. This is a true model, but we want to estimate it by f hat. If I want to make an analogy with philosophy, take a look at the philosophy of theory of ideas by Plato. Okay? It says that theory of ideas or forms by Plato. Plato was an ancient Greek philosopher. He said that soon whatever we see in this world, there is an ideal world where the forms or the ideas of whatever objects or whatever we see in this world can be found in that world. Okay? And for example, rooster has a true rooster in that world. Human has a true human in that world, something like that. This is in philosophy, ancient philosophy by Plato. It has some analogy with that too. So we have true model in the ideas world. We don't know that. We want to estimate it in this Earth world, and that's f hat. Okay. Then we do not have access to it, so we don't have access to this ideal f, so it's unknown. Okay. Also, the pure outputs, true observations of this f are not known, are not available, because actual f is not available, right? The output may be corrupted with an additive noise. So we have some, by the way, do you remember we have a data set? Recall preliminaries. We have some data set, x and y's. X inputs, y's can be the labels or the labels, for example, for regression or classification. So the labels can be either discrete or continuous. Do you remember? And xi's are the data, input data. So we have them. By the way, but we know that yi is not necessarily equal to fi. There might be some noise, additive noise. So yi is fi, actual fi, which we don't know, plus some eta I, or whatever we call it. And the noise is a Gaussian noise with mean 0 and variance sigma squared. Okay, this is clear. We have this, we saw that, and we know that the noise is Gaussian, this has Gaussian distribution. Therefore, expectation of the noise is 0. Okay, the mean of the noise is 0. The expectation of epsilon squared, the noise is squared. What is that? Recall the formulation for variance. Variance was equal to expectation of epsilon squared minus expectation of epsilon squared. If I rearrange that, do you remember? I talked about it. Don't you remember? Why you look at me like that? You remember what was variance? Variance of x was expectation of x squared minus expectation of x squared. Okay, rearrange that term. It becomes like this: variance of epsilon plus expectation of epsilon squared. I know that this is 0 because of this. So this is variance of epsilon, and variance of epsilon is sigma squared, right? Right. The true observation Fi is not random. See? Here we have noise for Yi, not for Fi. Yi is Fi plus epsilon I. There is no, so expectation of Fi is Fi. It's not a random variable. The output, the input training data goes from 1 to n, and their corrupted observations, or the labels, whatever we call it, the outputs, are available to us, okay, because of the data set. We would like to approximate or estimate the true model by a model F hat, okay, in order to estimate the observations. So we have some training data point, training data set, xi and yi's. For test phase, we want to have xi's, feed xi's as input and out predict yi's, right? Okay, so this is what we want. And these predicted yi's, just call them yi hat. Okay, we want yi hat to be for the training data. We want that to be as close as possible to yi. For the training data, yi hat needs to be close to yi, right? For the training data, we train the model using by the way, for example, do you remember the machine learning model, such as neural network or whatever we have? Yi's are the labels of the data set. Yi hats are the outputs of the model, such as outputs of neural network, output of machine learning model. And they need to be close to each other. The output should be close to the actual labels. Okay. We train the model using the training data in order to estimate the true model, right? After training the model, it can be used to estimate the output of the model for both the training input and the unseen test input. Let it be m number of test points, m. Okay, to have estimates yi from I to n and yi hat from 1 to m. So we want to have yi's for both training and test data. And why do we call test unseen? Because it's not seen in the training phase. We didn't use that in the training. Here we denote the estimation of the observation of the ith instance with either yi hat or fi hat. So you don't see, we have fi here, we don't have fi hat. I can also call it fi hat, doesn't matter. Right? Clear? Then the model can be a regression model, prediction model, or classification model. In regression, the model's output is continuous, in classification is discrete. The definition, do you remember? We had this in preliminaries. Yeah, so we have the relation between bias variance and mean squared error of the f hat. That's correct. F was not random, but f hat is. Okay. Mean squared error of the estimation of observation. I think when I told you that I want the output of the model, yi hats, to be close to yi's, I think the first thing which came to your mind is that let's minimize the mean squared error between them. Something like that. Okay, let's do that. Let's see what happens. Suppose we have an instance x0, y0. Consider an instance. Two cases might happen. This instance can be either a training point or a test or validation point. So if it is test or validation point, it's not used in training. Training point is used in training. Okay. We will cover both cases. According to equation 1. So do you remember what we had? yi equals fi plus epsilon I. Now for x0, y0, we have y0 equals f0 plus epsilon 0. Assume the model's estimation of y0 is f0 hat. Okay, or y0 hat, doesn't matter. The mean squared error of the estimation is this. This is mean squared error, right? Expectation of f0 hat minus y0 squared, right? According to this equation we can replace y0 with this, with f0 plus epsilon 0. So we have minus f0 minus epsilon 0. Okay. And then let's consider this as a term. Consider this as another term. Use the binomial thing. A plus b squared is a squared plus b squared plus 2ab. We have this squared plus the second squared minus 2, the first one, the second one. Here. Okay. Now, expectation is a linear operator. I can apply it on each of them. Expectation of the first term plus expectation of the second term plus expectation of the third term. Okay. Now, what is it? So this is I'm repeating. This I just showed in the previous slide, which is sigma squared. Why? Because of this. Here, we just showed that. Right? Expectation of epsilon squared is sigma squared. Then I'm repeating this also here. The last term, let's take a look at the last term, which is this. What do we have here? I can replace epsilon 0 with y0 minus f0 according to this equation, because y0 was f0 plus epsilon 0, right? Clear? Okay. Now for calculation of this term, we have two cases. We have two cases. Either the instance is in the training set or not in the training set. We'll see that how these yield to overfitting, cross-validation, and everything. Assume case 1 is instance not in the training set. Not in the training. It's in the test or validation. Right? Assume the instance is not in the training set, that is, it was not used for training the model. In other words, y0 is not in the training set. See, capital T here is a training set. Okay. This means that the estimation f0 hat is independent of the observation y0. Right? Notice that y0 is outputted by the trained model. When y0 hat is outputted by the model for the x0 hat, x0, we know that y0 hat and y0 are independent. Why? Because it wasn't seen in the training data. y0 is generated by the trained model, but we didn't use x0 for the x0 and y0 for the training. Therefore, y0 hat is independent of y0. Clear? When we don't use it in the training phase, it doesn't impact the trained model. They are independent. Okay, because the observation was not used to train the model, but the estimation is based from the model. Okay, obtained from the model. Therefore, we have this. This is from trained model. This is what we have. This is from trained model, but we didn't use y0 in the training. That's why they are independent. As y0 and f0 hat are independent, I can also have minus f0 from the side. I can subtract f0 from the sides of this equation. So I will have y0 minus f0 is also independent of f0 hat minus f0. Here, if it's not clear, please let me know. Therefore, expectation of this. We had this in the last term. Do you remember? You remember? We had this in the last term. Therefore, this expectation can be written as expectation of the first term times expectation of the second term. Recall preliminaries. When x and y are independent, expectation of xy equals expectation of x times expectation of y. What is this? This is 0. Because f0 is y0. Do you remember? F0 is y0. No? Wait. Because of this, sorry. All right, thank you. So expectation of y0 minus f0. This is a linear operator. Expectation is a linear operator. I can write it as expectation of y0 minus expectation of f0. What is expectation of y0? F0. Do you know why? Do you know why? Because of this. What was y0? What was y0? f0 plus epsilon 0. What was expectation of? So I can write expectation of y0 as expectation of f0 plus expectation of epsilon 0. What is expectation of epsilon 0? Is 0. We saw that because it's a Gaussian distribution with mean 0. Expectation of f0 is also f0 because it's not a random variable. F is not a random variable. Therefore, it's f0. So I can replace these with f0. Also, I know expectation of f0 is f0. So it's f0 minus f0. Therefore, it's 0. Right? Therefore, I can put 0 here. Please see that. Please see. Did you follow? If you didn't follow, please let me know. Where didn't you follow? Then it will have 0 times something, it will become 0. Okay, so it means that the third term, which was this in equation 5, or equation 6, is 0. When it is not in the training data set. You get it? Therefore, in this case, the last term is in equation 5 is 0. Therefore, the equation 5 is simplified to this. So this is mean squared error, by the way. This is mean squared error. Do you remember? This is mean squared error. Therefore, expectation of f0 hat minus y0 squared is expectation of f0 hat minus f0 squared plus sigma squared. Right? We found this. I'm repeating it here. Suppose the number of instances which are not in the training set is m. We have m test or validation data. Okay, not one, m of them, maybe. We can sum the mean squared error over all of them. The mean squared error of the first one, second one, third one. So we'll have this. Then what? So we'll have summation over this becomes summation over this plus summation over this. What is this, by the way? This is not related to I. Therefore, we'll have sigma squared. We can write it as sigma squared sum of I from 1 to m 1. This is m, so we'll have m sigma squared. Okay. The first term, which is this, is the error for the training data. Why? This error is referred to empirical error or training error, and is denoted by. Sorry. This term. I apologize. This term. The first term is this, right? The first term is the error for the training error. We can write it as error, small error. The second term is the error for the testing or validation error. I think, let me think, I got confused here. I got a bit confused. Okay, sorry. This term, summation of fi hat minus y high. Do you agree that this is the training error? This is summation over f0 and y0. F0 and y0 is not in the training. Fi and yi are in the training. Okay. So fi's and yi's are in the training. F0 and y0 is not in the training because we assume that they are not in the training. Right? This is test. This is train. I write the error of the training error by capital error, the error of the test error by a small error. You get it? You get it? So I can write it in this way. This is true error. This is the empirical error. Now let's go to the case 2, instance in the training set. What is it? Consider a multivariate random variable z whose components are independent random variables with normal distribution, such as this. So we have a multivariate Gaussian distribution. Each of the elements is a Gaussian distribution. Okay. Take mu as a vector, d-dimensional vector, and g of z from g1 to gd be a function of the random variable z. This, I'm defining something named Stein's lemma. Why am I defining this Stein's lemma? Stein was a mathematician. Okay. Because overfitting can be seen as a Stein's lemma in machine learning. We'll see that. Okay. In statistics, equation 10 is the Stein's lemma. This is called also called Stein's unbiased risk estimate. By the way, who found out that the overfitting is equivalent to Stein's unbiased risk estimate or SHORE machine learning? It was Professor Ali Quds. That was an interesting finding. Okay, you can see our tutorial on theory of cross-validation, regularization, bagging, and boosting for proof of equation 10. I don't know the proof here because it's out of the scope of this course. Okay. If the random variable is a univariate variable, Stein's lemma is this. We are gonna use equation 11. So equation 10 is for multivariate. Equation 11 is for the univariate. Okay. Now we had this. This was the Stein's lemma for univariate. I'm repeating it here. Now let's go back to our problem. We said that soon case 2 instance is in the training set, right? Suppose we take epsilon 0, 0, and f0 hat minus f0 as the z, u, and gz in this equation, in this short Stein's lemma. Let's use that, and then we'll see. Okay, so I have, what is z? Epsilon 0. Okay, I'm putting it here. Mu, I set it to 0. Gz, I set it to f0 hat minus f0. Okay, I'm just replacing things in the Stein's lemma. Then the right-hand side of the Stein's lemma is this. So sigma squared expectational derivative of f0 hat minus f0, which is this, with respect to epsilon 0. Z is epsilon 0 here. Okay. Sigma squared, then I can write this as derivative of the first term with respect to this minus derivative of the second term with respect to that, because derivative is a linear operator. Do you agree? Do you follow? Do you follow? Please give me feedback. No, you don't follow. Where didn't you follow? Where didn't you stop following? What? What? Can you answer me? When didn't you stop? Okay. Let me go back a bit. Case one. Case one was clear, right? Okay. For case two, I said, which case two instance is in the training set. For case two, I need something named Stein's lemma. I need something from mathematics. I showed you that this is Stein's lemma for, this is a formula for mathematics. For multivariate, for univariate is equation 11. I didn't prove it. I said you can see our tutorial for proof. Okay, I'm gonna use this. I'm gonna use it. How? I'm repeating the Stein's lemma here, right? I'm repeating it here. Then in Stein's lemma, we have several variables. If you see, we have z, we have mu, we have g of z. G of z is a function. Okay. Now let's replace these variables with what we want. Let's replace z with epsilon 0. Epsilon 0 is a noise, right? Let's replace mu with 0. Let's replace, by the way, mu is mean here because I don't care. I assume that mean is 0, the mean of the error, the noise. Right? That's fine. And also g of z is a function of z. Z was epsilon 0, right? I set it to epsilon 0. I assume that g of z is f0 hat minus f0. It's a function. I define it. Okay, so far clear? Now I replace in this Stein's lemma the variables that I set. Okay. The right hand side also I replace it. So far clear? Please, whenever you don't understand a part, let me know. Otherwise, how do I know what's going on in your mind? Please let me know, okay? Then, do you agree that derivative of a plus b with respect to something is derivative of a plus derivative of b? Because derivative is a linear operator. So I will have this. I will also have this. So far clear? Okay. Then, do you agree that this is 0? Because f0 is not dependent on the noise, right? Yes, exactly. So we'll have only this term. So far clear. Now, what do we have? Chain rule. Do you agree that I can write derivative of f0 hat with respect to derivative of epsilon 0 as derivative of f0 hat with respect to y0 times derivative of y0 with respect to epsilon 0? Chain rule. Derivative of Benjamin with respect to desk. You can write it as derivative of Benjamin with respect to table, derivative of table with respect to desk. Okay. So then what do we have here? This is 1. Why? Because y0 was epsilon 0 plus f0. This is, therefore we'll have this. So far clear. Therefore, what is this, by the way? This is actually the third term. The third term. This is the third term. Do you remember? The third term. Now I think you understand why I chose those variables in the Stein's lemma. Because I wanted to generate the third term in the left-hand side of a Stein's lemma. You get it? No? Guys, listen to me. We had a third term in the mean squared error. So because we want to minimize the mean squared error between the actual labels and the output of the model. This is where we started. Okay, we simplified that. It has, this mean squared error has one term, the first term, the second term, the third term. My focus is the third term. Two cases happen. Either that point is in the training data set or not. For the third term, for the case where we are not in the training set, I simplified that. And we came up with equation with this. We saw that the third term is 0. So the mean squared error got simplified to equation 7. Also, in the second case where the data point is in the training set, okay, then I said I'm gonna use some formula for mathematics named Shor or Stein's lemma. How do I choose the variables in that formula in order to generate the third term of mean squared error that I had? If I put these variables as these, I will get the third term. Using that formula from mathematics named Shor or Stein's lemma, we'll see that this is equivalent to this. Okay, now I put the third term back in the mean squared error. Gives me equation 12. The mean squared error becomes something for case 1, becomes something for case. We had this, I have repeated it here. Then what happens here? I can, again, as before, I can have summation. So this, if I have the summation for i's, I know this is a training error. For zeros, is, this is the test error or a small case error. I have my n squared here. I also have this term. By the way, here, this is error, this is error. I'm bringing these to the other side of the equation. That's why this minus becomes plus and this plus becomes minus. In basic words, in simple words, I have two equations. Equation 9 for case 1. Equation 14 for case 2. And now I'm gonna tell you why it is related to overfitting. By the way, if you didn't understand the proof, that's fine. But I think I'm going to record one more video offline and explain in more detail that the best way that I can upload it. So I think that will help you guys to understand better. But I tried my best to explain it, but I think I need to think a bit more how to explain in a clearer way, more clear way. I will record that, I will put it on YouTube. I will give you the link for that. Again, if you didn't understand the proof, that's fine. Interpretation is important. Okay, let me interpret it for you. Okay. We came up with this, right? We came up with it. You will see how I'm gonna justify overfitting, regularization, and everything. Loss functions of neural network with everything, many things with this. The last term, what is the last term? The last term in this equation is a measure of complexity. Can you tell me why? Complexity of the model. Whether the model is simple or complex. Can you tell me why? Because it's derivative of output of the predicted labels with respect to actual labels. If it's too complicated, too complex, this might blow up. If it's a simple thing, what does it mean? It means that from point to point, actually, if you change the true model, how much does it affect the predicted model? How complex is it? If it's not too complex, this derivative is low. If it is too complex, this blows up. As you see in the error, there is a measure of complexity. Okay. The last term is the measure of complexity, also called the measure of overfitting. Okay, we'll see. Of the model. Note that this means that if we move the ith training instance, how much the model's estimation of that instance will change. This shows how much the model is complex or overfit. For better understanding, suppose a line regressing the trend. So assume that, consider figure 1. Consider figure 1. I don't know if we can see that or not. This is a green point. The other points are black. Okay, the other points are black. Then assume the green point is a training point here in A and B. Okay, and I'm fitting one line, a linear line, to the data. This is called linear regression. Okay. We will go over linear regression, but I just want you to understand what overfitting means. Here, I changed my data point, one of the training points, to here. So I move it down. It becomes here. So I move this training point down a bit. How much does it change the line? Not much. Not much. Why? Because the model is simple. Model is simple. Let's consider a too complex regression model, such as a neural network. Complex, a non-linear regression model, which is too complex. When we say too complex, it passes over all of the data points, training data points. In linear regression, it doesn't care whether it passes over all of the data points. It actually can't, because it needs to be linear. It takes an average impact. But in complex case, it passes through all of the data points. Then if I move this, it ruins the model. If I move this, because in case C, it's going up. When I move it down, the whole model goes down, because it needs to pass through that. Why did it happen? Because the model was too complex. And now you see that this last term in the error is showing that the amount of complexity. This figure A and B, these two are called underfitting. Underfitting. Because they are so these C and D are called overfitting. So compare underfitting and overfitting. In the middle, there is something named good fit. We don't want to be too simple. We don't want to be too complex. We want to be something in the middle. Good fit. Right? Yes. I think someone with showed with finger. So I think this might be a good fit. Might be good. Not linear, not too complex. Okay, so we talked about underfitting and overfitting. Now, we had this, I'm repeating this here. According to this equation, in the case where do you remember this equation was for when data was in the training set? Do you remember? In the case where the instance, why do you laugh? Okay.
When you read the slide, everything's gone.
Guys, we had two cases. One case where the data was not in the training.
Oh, and one
case where the data was in the
training.
This equation was for when the data was in the training. Was in the training.
Yeah.
Okay, according to this equation, in the case where the instance is in the training set, the empirical error. So this is a true error. This is empirical error. We don't have the true error. We have the empirical error in practice. With the true error is for the ideal error in the world of Plato. Okay. So we have empirical. These two are not a good estimation of each other, because we have some pain in the neck term. Okay. So the empirical error is not necessarily a good estimation of true error, because we have a term dependent on the complexity. Okay, that's what the thing. The reason is that minimization of error usually okay, then another thing. There is a trade-off. You can't have the perfect thing. Perfection is not possible here. you want to reduce this term error, this goes up. See, you reduce the empirical error, hoping that the true error also goes down. However, at some point you will see complexity goes up. Okay, I think I need to quote something again from philosophy. I think this is related. So Galileo said that the language of the world is mathematics. I think that's true. But physics and all of things are based on mathematics. Okay, and that's why. And we know that in a real world, whenever you get something, you lose something. This is actually, I think, in Hinduistic and Buddhism. In Hinduism, Buddhism, they also talk about these things. So, whenever you get something, Confucius, I think, talks about that too. Whenever you get something, you lose something in the world. Never this happens that you get something and you don't lose anything. This is in philosophy. And according to what Galileo said, math is the world, is describing the world. So in mathematics also this is true. Whenever you get, you lose something. Some examples. Whenever, for example, in machine learning, actually, in machine learning, you have a linear model, you have a simple model, it works very fast. And however, there is a problem that it can't work on the big data. Okay. You make it more complicated, such as, for example, you make it a neural network. Okay. You make it a neural network. You make it complicated. Then it works on the nonlinear data and big data, everything. Well, you must have lost something. What have you lost? No. It became complex. You lost the speed. It takes time to train the neural network. The simple model was trained in a few seconds. As you see in machine learning, in mathematics, in everything. Whenever you get something, you lose something. Also, it's shown here too. Okay. Just give me. When did it stop sharing? So I know you're tired. I'll try to wrap it up. Just give me some. If the model is trained in an extremely simple way, so that its estimation has low variance but high bias, underfitting. You remember variance and bias? So underfitting has low variance, high bias. This question is asked a lot in interviews. Okay. Underfitting is also called overgeneralization. In overfitting, it's the other way around. You have high variance, low bias. So I think these two sentences are very important. Underfitting, low variance, high bias, low complexity. Overfitting, high variance, low bias, high complexity. Do you know why? The reasoning? The reasoning is that you can see it in this figure too. C and D. You are overfitting, right? You are passing through all of the points. You have a lot of variance. See my hand? It's variance. Right? Let's first talk about variance. Here, in underfitting, just a line. It's not going up and down. Low variance. In underfitting, we have low variance. And bias. Let's talk about bias. What is that? So we have high bias here because here we have low bias because we are passing through all of the points. So we are not missing anything. Here we have high bias. We are taking an average impact, something like that. See? That's the reason. I think by this figure, you can understand the reason. Okay, so I think, I don't know if I could explain well or not. I apologize if I couldn't. I know it, I wasn't satisfied with myself this session, but I tried at least. I will record a complete session on this slide deck. I will upload it on YouTube, and I will ask both the students of both courses to watch that. And I think that is good to know. I will not test you on the proofs and these things. I just, why do I provide the proofs and these things? Sometimes it might get complicated, because for you to understand the complexity and these things, why this is happening, why the true error is not the empirical error, because there is a complexity term. And where does it come from? The Stein's lemma. The Stein's lemma in mathematics. What?
Point is in the second situation when second case that we took.
Yeah. And this actually doesn't happen. I think I have some slides to talk about that too, but I will record it. But this in the test phase, we don't have this term of complexity. Do you remember what was in the test phase? Equation 9, case 1. When data point is a test point, right? We don't have any term for complexity. What does it mean? Actually, the empirical error is a good error, good estimation of the true error. But in the training, we should be careful that whatever we train, we might increase the complexity. In the test, we don't have this concern. Now I think you understand the difference of these two cases, right? Again, I will record it, and thank you for your attention. I finished it a bit sooner because I know you're tired. Thank you.